Now that we know how to calculate the magnetic force exerted on a moving charge or a wire with a current, we will learn how to find the magnetic field created by charges and the current. For example, suppose we wish to find magnetic forces between two wires carrying electric currents, I1 and I2. Wire with current 1 will experience a magnetic force created by a magnetic field of wire 2. At the same time, wire with current 2 will experience magnetic force created by field of wire 1. We have already learned how to calculate the force on the wire if we know the current through the wire and magnetic field. The force is obtained by dividing the wire into many small elements ds, calculating the force on each small element IDS cross B, and integrating the elementary force over the whole length of the wire. While each elementary current ds feels magnetic fields created by other currents, it also creates magnetic field of its own. The magnetic field created by the elementary current is given by another formula called the Biot-Savart law. Two French physicists, Jean-Baptiste Biot and Félix Savart, discovered a relationship between the strength of electric current and strength of magnetic field created by this current in 1820. If we take a small element of the wire ds and multiply it by the current that flows through this element I, we obtain what is called an elementary current I times ds. The magnetic field created by elementary current is given by this formula. dB is equal to mu 0 over 4 pi times I times ds cross r hat divided by r squared. The magnetic field described by this law is the field due to the current carrying conductor, specifically due to this elementary current IDS. You shouldn't confuse it with the field created by other conductors that is felt by ds and creates magnetic force on IDS. Let us now understand various terms in this formula. First of all, dB is measured at point P at distance r from the elementary current I times ds. R hat is the familiar unit vector pointing in the direction from IDS to P. It is given by the total vector r divided by the length of r. If theta is the angle between the vectors ds and r, then the magnitude of the field is given by mu naught divided by 4 pi r squared times I times magnitude of ds times sine theta. The direction of the field is found from the right-hand rule, so therefore the total formula takes the expression on the left. Finally, mu naught is the unit conversion constant that depends on the chosen system of units. It is similar to the constant epsilon 0 that is introduced in discussion of electricity. The constant mu naught is called permeability of free space. In the SI system of units, mu naught is equal to 4 pi times 10 to the negative 7 Tesla times meter divided by amperes. This is just a constant to convert between convenient units, measuring the current in amperes and magnetic fields in Teslas. dB is not the total field created by the wire. It is just a wee element of the field created by an elementary current in the length segment ds. To find the total field, you need to sum up all contributions from the elementary currents I times ds. So the total field is given by an integral of mu naught I divided by 4 pi times the integral of ds hat cross r hat divided by r squared. This integral is over in the entire length of the wire or entire current distribution. In deriving this formula, we use the fact that I is the same through the whole length of the wire. The current doesn't disappear. Therefore, I is the same for every element ds and can be taken out of the integral. Let us consider several examples. First, let us calculate the magnetic field created by a straight conductor of length L. We select the x-axis to be parallel to the conductor. Next, we compute the magnetic field at point P at distance a from the conductor. Point P does not have to be above the middle of the conductor. But for convenience, we select the origin O, corresponding to x equals 0, to be exactly below point P. To find the total magnetic field at P, we break the conductor into many small elements ds, such as the one shown in the figure. We first need to find the distance r and the unit vector r hat from ds to P. The length ds is simply equal to dx, so we could perform integration over dx from the left to the right end of the conductor. But instead of integrating over dx, in this case it is more convenient to integrate over the angle theta shown in the figure. The angle theta is between the line connecting ds and P and the vertical line dropped from P to the conductor. The vector product ds cross r is perpendicular to the plane of the screen. It is proportional to the unit vector k hat along the z-axis. The magnitude of ds cross r is equal to dx times cosine theta. Now let theta 1 and theta 2 be the angles between the vertical line from P to the conductor and directions to the left and right ends of the conductor. Tangent of theta is equal to x divided by a. Therefore, dx over a is equal to d theta over cosine theta squared. We can use this relation to set up the integral for the total magnetic field. It is given here. The integration is of cosine theta times d theta from the angle theta 1 to theta 2. I can be taken out of the integral. The full expression for this integral can be evaluated as mu naught times I divided by 4 pi a times sine theta 1 minus sine theta 2. If theta 1 is larger than theta 2, B points out of the screen, as shown in the figure. Otherwise, if theta 2 is larger than theta 1, this expression is negative. B points into the screen. So here we obtained magnetic field of a wire of an arbitrary length L. This expression further simplifies if we measure the magnetic field very close to the wire. That is, if we assume that the distance A is much smaller than the length of the wire L. For example, if the length of the wire is 1 meter and we measure the magnetic field at the distance of a few centimeters, this approximation will certainly apply. In this case, the angle theta 1 is approximately equal to plus 90 degrees and the angle theta 2 is equal to minus 90 degrees. We evaluate the expression for B using these values of thetas, and we get B equals to mu naught times I divided by 2 pi a. So the magnetic field for an infinitely long wire depends only on the strength of the current and the distance from the wire. The length of the wire doesn't matter. The direction of B of an infinitely long wire still obeys the right-hand rule. In this case, the direction can be found using another convenient rule of thumb. If we take our right hand and point the thumb along the direction of the current, and then 4 banded fingers of the right hand will point in the direction of B. The field lines of B are concentric circles centered on the long wire. The field lines are perpendicular to the wire. The magnetic field depends only on the distance A from the wire. It is independent of the height along the wire. Another easy configuration to calculate is a thin wire with current I that is curved as an arc AC of a circle of radius A that subtends an angle theta. Let us find the magnetic field at point O due to the curved wire segment only. Again, we break the whole wire into small elements ds. The distance from each element ds to the point O, called r, is the same for all elements. It is simply equal to the radius a of the circle. By the right-hand rule, B points into the screen at point O. It is easy to calculate the magnitude of B, which in this case is equal to mu naught times I multiplied by the angle theta and divided by 4 pi a. Theta here must be in radians. Please set up and calculate this integral. Using the previous example, we can easily calculate the magnetic field at the center of a circular loop of wire. For this case, we take theta equals to 2 pi. But now 2 pi in the numerator cancels with 4 pi in the denominator. The full field is equal to mu naught times I divided by 2a. This is the field at the center of the loop, exactly in the plane of the loop. Of course, it is also easy to calculate the magnetic field at point P on the central axis of the loop, but not exactly at the center O of the loop. In this case, only the x component of the field is non-zero. Components that are perpendicular to the axis cancel because of the symmetry of the system. Do this calculation by yourself. The x component in this case depends both on the radius a of the loop as well as the distance x from the center. If we set x equal to 0, we recover the previous result, mu naught times I divided by 2a, the field at the center of the loop. As you see in this example, the magnetic field on the axis depends only on x squared, not on x. It always points in the positive x direction, regardless of whether the loop is to the left or to the right from the measurement point. If we stack several loops with the same current I together, their magnetic fields on the axis will add up. This principle is used to create strong magnetic fields in devices called electromagnets or solenoids. A solenoid is a long wire wound in the form of a helix. If the wires are tightly wound, a reasonably uniform magnetic field can be produced in space surrounded by the turns of the wire, called the interior of the solenoid. The magnetic field lines enter the solenoid from the bottom and exit on the top. The magnetic field lines are approximately parallel in the middle of the solenoid. To emphasize it again, the field lines in the interior of a well-built solenoid are nearly parallel to each other, uniformly distributed, and close together. This indicates that the field inside the solenoid is strong and almost uniform. Irregularities of the field decrease as the distance between the turns decreases and the solenoid gets longer. In the limit when turns are very close and the solenoid is very long, the field distribution of an electromagnet is similar to that of a bar magnet. It has a north pole where the field lines come out of the solenoid and south pole where field lines come in. As the length of the solenoid increases, the interior field becomes more uniform, the exterior field becomes weaker. In the limit of an infinitely long solenoid, the field is non-zero only in the interior. Imagine now we construct a perfect or an ideal solenoid. The field inside the ideal solenoid is perfectly uniform. An ideal solenoid is approached when the turns are closely spaced, the length L of the solenoid is much greater than the radius R of the turns. In this figure, we show the cross-section of the solenoid. Each loop is indicated by two circles with the current coming out and going into the plane of the cross-section. The total number of turns in the solenoid is denoted by capital N. What we mean here is that both length L and the number of turns N are very large, practically infinite. But the ratio N divided by L, the number of turns per unit length, is finite. It is relatively easy to build real-life solenoids that are quite close to this ideal case. We can obtain the total field inside an ideal solenoid by summing magnetic fields of many circular loops using the formula derived in example 3. In that example, we found that magnetic field on the central axis of one loop is equal to mu naught I times a squared divided by 2 times a squared plus x squared to the power 3/2, where a in this case is the radius r of the solenoid. X is the distance from the loop to the point of measurement along the axis of the loop. If we take length dx of a solenoid, there will be n times dx loops within this length, where n is the number of turns per unit length. the magnetic field contributed by length dx is equal to the magnetic field of one loop multiplied by the number of loops within the segment. By summing integrating over all loops of the solenoid and assuming L goes to infinity, we can obtain the formula for the total magnetic field inside the solenoid. It is given by mu naught times I times lowercase n. To summarize, the magnetic field near the center axis of a very long solenoid with current I can be written in two ways, either as mu naught times capital N divided by L times I, where N is the total number of turns in the solenoid and L is the total length, or as mu naught times lowercase n times I, where N is the number of turns per unit length. This approximation works very well for professionally built solenoids.